Hi guys and welcome to AP Statistics Linear Regression. Today we're going to be talking about residuals. By the end of today's lesson, you should be able to create a linear model with summaries. You should be able to determine residuals, and you should be able to interpret residual plots. Now, residual plots are probably one of the more important things that we're going to be looking at, so this is a very important skill. So we're in chapter 8 and 9 if you want to follow along in the book, and everyone should be working on their linear regression homework packet. So we already know that when we come up with a regression line, we're going to have the form of y hat, which is our model, is going to equal a plus bx, where a in this case is the y-intercept, which tells us where the line crosses the intercepts in the y-axis. And we could always find the y-intercept by using this formula, where a equals y bar, the mean of our response variables, minus the slope times x bar, the mean of our explanatory variable. The LSRL, or the least squared regression line, will always pass through the mean of our x and our y. In other words, the LSRL will pass through the point x bar, y bar. This is in the units of y, of course. B is our slope, which tells us how rapidly y hat changes with respect to x, where y hat is our predicted response variable based on our explanatory variable. There's also a formula for the slope where b equals r, the correlation, times the standard deviation of y over the standard deviation of x. The slope is always in units of y per x. So let's say, for example, I wish to determine the model of a relationship of the scores between the first exam given in AP Calculus and the score that they receive on their AP exam. So the summary for a random sample of students over the years is given below. So the average for a random selection of students of their first exam in AP Calculus is approximately 55.74 with the standard deviation of 14.51. For those exact same students, the average AP exam score is 3.67 with a standard deviation of 1.49. The correlation or the strength of the relationship between these two variables is approximately 0.83, which is a fairly strong positive linear relationship. Given that the data is approximately linear, calculate the slope of the regression line. So in order to do that, we're going to use our formula. So B equals the correlation R times the standard deviation of y divided by the standard deviation of x. So in this case, it's going to be 0.83 times 1.49 divided by 14.51, which is approximately 0.085. So let's go ahead and interpret the slope. For every increase of 1 point on the first exam, our model predicts an average increase of 0.085 on the AP exam. So we know that if one student scores approximately 10 points more than another student on the first exam, we should expect their AP score to be approximately 0.85 greater on the AP exam. Now, obviously, you can't get a 0.85 on the AP exam, so it's going to give us a rounded approximation of what kind of a score we should expect to see. Let's go ahead and determine the y-intercept using our formula as well. So our formula is a equals y bar minus bx bar. So a in this case is going to be 3.67 minus the slope of 0.085 times 55.74, the mean of our explanatory variable, which is approximately negative 1.068. Let's go ahead and interpret this. With a score of 0 on the first exam, our model predicts a score of negative 1.068 on the AP exam. Of course, this makes no sense at all because the lowest score you could actually get on the AP exam is 1. That also tells us that we're not likely to see a score of 0 on the first exam. More than likely, some students will get some points, so we should rarely ever see a score of 0 or anything even close. So let's go ahead and determine the equation of our LSRL now that we have our y-intercept and our slope. So the AP exam score hat, or the approximated AP exam score given our model, is approximately negative 1.068 plus 0.083 times our first exam score. So if a student scored 65 on the first exam, what does our model predict for this student on the AP exam? So if we just substitute in 65 into our model, we get that our predicted AP exam score would be approximately 4.327. Now, of course, you can't get a score of 4.327, and so this is an average. So if we took an average of several students who scored 65, we would see that our model would predict an average score of 4.327. So the following is a scatter plot of total fat versus protein for 30 items on the Burger King menu. So our explanatory variable in this case is protein and the response variable is fat. So what we want to do is we want to use protein. If we know how much protein is in an item, we want to see if we can predict how much fat is also in that item. So how do we interpret the association with a correlation of 0.83? So with a correlation of 0.83, there's a fairly strong positive linear association between grams of protein and grams of fat. The regression line for the Burger King data fits the data well, and we get this equation that fat hat, or the predicted amount of fat, is equal to 6.8 plus 0.97 protein. Let's go ahead and use the LSRL to predict the amount of fat content there is in a BK broiler chicken sandwich with 30 grams of protein. So if we substitute in 30 into our formula, we get that the approximate amount of fat, or the predicted amount of fat on average for an item with 30 grams of protein, should be approximately 35.9 grams of fat. So a residual is the vertical distance from a point to the line, specifically our LSRL. It's a difference between the observed value and the associated predicted value. So residual specifically is observed value minus predicted value. We use the letter E to represent residuals. So E is equal to the observed, or the actual value, minus Y hat, or the predicted value. A negative residual means that our prediction was an overestimate and our actual value is lower or below the LSRL. A positive residual means our predicted value is too small and it's an underestimate, and that means that our actual value is above the LSRL. In the graph above, we can see that the BK broiler estimated that there was going to be approximately 36 grams of fat. Well, in actuality, it had 25 grams of fat. So if we take the actual, which is 25, minus the predicted of 36, we get a residual of negative 11 grams of fat. Sometimes it's difficult to determine if a function truly is linear. For example, if you look at a quadratic function on an interval from 10 to 11, it actually looks linear, but in actuality, it's not. So a residual plot will help us to determine the actual linearity of a data. A residual plot is the graph that shows the residuals on a vertical axis and the independent variable on the horizontal axis. A random scatter in the residual indicates the data is linear and the LSRL is an appropriate model. So if we see a residual plot that looks something like this, where it's a random scatter about this line, which this line does represent our LSRL, we would say that the data is somewhat linear. So this is a random scatter and it indicates that the LSRL is appropriate. If you see something like this where there's a definite curve in the data, we're going to say that the data is actually not linear. So this shows a curved pattern and it indicates that the LSRL is not appropriate because the data is actually curved. In this case, we're going to want to use some kind of nonlinear regression. This also shows a curved pattern and it also indicates that the LSRL is not appropriate. So we always want to look at the residual plots to determine if the LSRL is appropriate. If you see a curved pattern, we're going to say that it's not appropriate. If you don't see a curved pattern, if you see a random scatter, then we're going to say that the LSRL is appropriate. And we're going to say that the data is relatively linear. So here's the residual plot for Burger King's menu. The regression shows a random scatter, which tells us that LSRL is a good model and that the data is linear. The relationship between grams of protein and grams of fat does seem to have a linear relationship. So check to make sure that the residual plot has the same amount of scatter throughout. And so this is going to be something called an equal variance assumption. Does the plot thicken condition? What we don't want to see is this fan shape. And so you don't want to see these data points getting further and further away from our LSRL. What you do want to see is a random scatter, and you want it to be fairly uniform throughout the entire graph. The residual plot shows a random scatter, so it does tell us that the data is linear, However, it does not have equal variance. So a thickening plot tells us that as the explanatory variable gets larger, our prediction or our estimate gets less and less reliable. So let's determine if the LSRL is appropriate given the following residual plots. If you see something like this, we could see that there is a definite curve. And so this right here has a definite curve. And so the least squared regression line would not be appropriate. This data is not linear. If you see data like this also has a definite curve. And so we're going to say that the LSRL is not appropriate and the data is not linear. So this data is not specifically curved, it is linear, but it is not a random scatter. So if you see something like this, the LSRL that we created is not appropriate for this data. This is what it might look like if we were to use our calculators. If you see something like this, I would say that this is a random scatter and the LSRL is appropriate. In this case, some of you guys might want to connect the dots, and that's not what we're trying to do here. We're not trying to connect dots. We just want to see in general, do these points match a random scatter or does it show us a definite curve? And when we say a definite curve, we're really talking about some kind of U shape or some kind of N shape. In this case, I don't necessarily see a curve, a U shape. This might have some kind of U shape. I'm not really sure. But what we're looking for is a random scatter in general here. In general, I would say that the LSRL is appropriate for this. However, it's possible that this might have some kind of U shape or some kind of curve to it. And so I'm going to say that the LSRL may be appropriate for this case. So for this last one, we have very few data points. And since we have such few data points, it's very possible for me to draw a curve in here, or it's very possible for there to be a curve in here. It's also very possible that this is a random scatter. I'm really not sure. And so whenever we have a few data points, it's very possible we're making an inappropriate decision based on this data. And so I would always put a disclaimer with little data like this. And so I'm going to say that the LSRL may be appropriate. It's very possible that it is linear. It's also very possible that it's curved. Well, thanks for watching. I hope this was helpful.